For section 5, we finally get into some integration techniques rather than what we've been doing. So we're going to build some skills here and become more powerful calculus students in this section. And then you'll be able to stop bugging me about, is there a better way to do this type questions. The answer is no, by the way. I've taught you all the best ways so far. Anyway, so we have two parts to this section. There's part 1 and part 2. No. Pattern recognition is the first technique that you're going to learn, and then after that we'll get into integration by substitution. So the first thing we want to do is learn how to recognize patterns, and we've been doing that when we first started, before the end of the semester actually, when we were looking through that worksheet. We were using pattern recognition, so you kind of already have that idea. Pattern recognition just undoes the chain rule. So what you're looking for is the integral of some function composed of another function, and that function that's within the other function has its derivative sitting right here. If that pattern exists, then you can integrate it. Basically, the derivative of the function inside disappears, and you just integrate the outer function. You'll see what I mean in a little bit. Another way to look at the above theorem, so this theorem right here is this. If you let u equal g of x, then the derivative of u would be g prime of x dx, written as a differential right here. And if you substitute everything in, then you have the integral of the function with respect to u du, which you can do. You've been doing that, basically. It's just f of x dx, same thing. And then you integrate that function and you get that guy plus c. So, the idea here is not to get hung up on the language or the notation that you see. It's to recognize a pattern. You're looking for something that created a chain rule type situation, and you're just undoing that for the first part of this section. All right, I set it up like a tic-tac-toe board, but we're not going to play tic-tac-toe. We're just going to go ahead and do this. So for this first one, I want to notice that I have the integral of something times something sitting here. And if you notice, there's an inside function here. I got something raised to a power, and then the inside function sitting here, its derivative is 2x. So basically, what would I have to have if I took the derivative of an original function and got this sitting here? Well, I'd be undoing the chain rule if I did that. So the chain rule would say that the exponent was decayed by 1. I brought the exponent down, decayed the exponent by 1. What was inside stayed the same, and then I had to multiply on the derivative of what was inside. So I'm just undoing all that, okay? Which means, what? What was my original function? 1/3. Why 1/3? Because I should see a 3 right here, right? But I don't. Which means that I must have had a 1/3 hanging out in order to get rid of that 3. So I need a 1/3. Now what? Plus c. So let's check that to make sure that we did it right. If we were taking the derivative of this guy, then we'd use the general power rule, or the chain rule. The exponent would come down. 3 times 1/3 is gone. What's inside stays the same. Decay the exponent by 1, so you get squared here. And then you got to multiply in the derivative of what was inside, 2x, which is exactly what we started off with up here. So we did it correctly. This is the right answer. Next one. Again, we want to see that there's some sort of chain rule that happened here, and we want to undo the chain rule. Okay. So my original function would have been what sitting here? Sine 5x. If I integrate 5 cosine 5x, the cosine 5x must have come from a sine 5x. Now what happened to this 5? that was the result of using the chain rule. If I take the derivative of sine 5x, I need to make sine u, and then u is 5x, so then u prime is 5. So then the derivative of u times u prime gives me the 5 cosine 5x. I have to include the plus c here because that constant, if it was there, would have disappeared when I took the derivative. How about this one? So the first thing you want to notice is that the derivative of the inner function here is sitting out here. So the chain rule did happen, which means that this exponent must have been a 5. So I know I have the x squared plus 1 to the 5th. I know that the 2x is going to completely disappear. But when I take the derivative of this, the 5 would be out front, which means that I need to get rid of that 5 so that I wind up with exactly this, which means I need a 1/5, or put the whole thing over 5. A couple different ways you can write that. How about this one? We can rewrite it. If we rewrite it, we get the integral 3x squared times x to the 3rd plus 1 to the 1/2 dx. The 3x squared sitting here is the derivative of what's inside. So when I undo the chain rule, the 3x squared completely goes away. Okay, so we have to increase the exponent by 1. And there must be a 2/3 out front because when the 3/2 comes down, they need to form 1. So that I'm left with this to the 1/2 times u prime, which was 3x squared, plus c. So this one is the answer here. It takes a little bit of thought sometimes, but if you recognize the pattern that the chain rule was used, then the u prime will totally disappear. And then you work with this. This one. Do we have the chain rule sitting here? Do we have that pattern? But I can make it. I can make the pattern. What should I see out here as u prime? I should see 2x. If I put a 2 there, now I do have the pattern. But I've changed the whole integral. So what I really need to do is incorporate a fancy 1. If I put a 2 here, then a 1/2 out front will make basically a fancy 1. Because I can pull that 2 out, I can put that 1/2 in, and I've done nothing to change this thing, except make it look like the pattern. So now that I do have the pattern, what do I get? The 1/2 is still out front. Okay, the exponent's supposed to be 5, so I have x squared plus 1 to the 5th. But that 1/5 needs to go out front because of the fact that there was no 5 sitting here. Is that it? I need a plus c. And then we're going to reduce that. So 1/2 times 1/5 is 1/10 times x squared plus 1 to the 5th plus c. It is a very good idea to always check to make sure that you're doing these problems right, especially now in the beginning when you're first starting out. So let's check. To take the derivative of this, the 5 comes down. 5/10 gives me 1/2 x squared plus 1 to the 4th times the derivative of what's inside, which is 2x. So I have this 1/2 times 2x, which is just x, which gives me exactly what I have sitting right here. So this is the correct answer. Next one. Rewrite it. So we get the integral of x squared times x to the third plus 1 to the 1/2 dx. Okay. We gotta fix this so that the pattern matches. We need a 3 sitting here because the derivative of what's inside is 3x squared. So this needs to be 3x squared, which means I need a 1/3 out front to take care of that fancy 1. And now I'm pretty much ready to go. Okay, so I'm going to do this first. X to the third plus 1 to the 3/2. Now to get rid of that 3/2 when it comes down, I need to have a 2/3 sitting out front. Is that it? Plus c. Now simplify it. 2/9 times x to the third plus 1, 3/2 plus c. No. The c is probably 9/8. Probably not. It could be anything. If you want to make it 9/8 in your mind, go for it. Okay, a couple trig integrals to deal with here. The integral of secant squared x times tangent x plus 3 dx. I got u prime. The derivative of tangent x plus 3 is secant squared x. Pretty sure it is. So let's do an aside here. If I have the tangent x plus 3 and I want to take the derivative, what do I get? I get secant squared x. What happened to the 3? It disappeared. Okay? So yes, the derivative, the pattern is already here. It doesn't look like it is, kind of, but it is there. Come on. So what am I gonna write? Is it?
No, we have to. What is the H?
Remember that this is undoing a chain rule problem. So we had to do the chain rule in order to get this look to it. Which means that this is the function inside. The exponent here is 1. My exponent is going to increase to 2. So it started off as tangent x plus 3 squared. So then when I took the derivative, what had to happen? I needed a 1/2. So I could divide by 2. Now when the 2 comes down, the 2 over 2 goes away. I have the tangent x plus 3 inside times the derivative of what's inside, which is secant squared. So now I put the plus c on there and I'm good. Remember that the pattern is undoing the chain rule. So there had to be some sort of chain rule situation, and this is it right here. All right, so maybe we can do this one now.
It's not quite it, so we gotta change it, so it is.
The same thing without the 1/2. This is the thing inside. That must have been to the second. If I take the derivative of this, the 2 comes down. I have the 2 there, so I don't need to put the 1/2 in this time. The derivative of what's inside is the secant squared. So that's the answer. Okay, one more. Do we have the pattern, exactly. It's close. The derivative of what's inside is supposed to be 2x. I have the x sitting here, so I'm going to put a 2 there, which means I need to put a 1/2 out front. Now the pattern is there, so I can undo the chain rule. What do I get? So x squared plus 1 to the third. The 1/2 has to be there. The 3 would have come down, but the 3 wasn't there, so I also need a 1/3. Plus c, so this becomes 1/6 times x squared plus 1 to the third plus c. Again, check it to make sure. The 3 comes down, and I get 3/6, which is 1/2, times the derivative, or times what's inside, to the second power, times the derivative of what's inside, which is 2x. So I have 1/2 times 2x, which is just x, which gives me that, and then the rest is correct. You're going to want to check these for sure. All right. That last example, and actually several of the examples that we had in that block of 9 problems, the pattern wasn't always matched perfectly. So if everything matches except some constant multiple, this is very important, it's a constant multiple, then you can multiply and divide by that multiple to generate the pattern manually. You can trick it into giving up the pattern. Here it is again. So what was missing from this pattern? The 2. Which means that in order to keep this situation exactly as it was, the 1/2 goes out front. And now I have that matching pattern. And on this one, we had this one also. Is everything okay here? Yeah? Okay. So if I pull the 5 out, then I just have cosine 5x, but that doesn't give me the pattern. I leave the 5 in, and I have the pattern that I want. Sine 5x. The derivative of that means I need sine u, which gives me cosine u times u prime. U prime is the 5, so that gives me the 5 cosine 5x plus c here. On this one, once you have the pattern, you get x squared plus 1 squared, but it turns into the third. I have the 1/2 out front. The 3 would have come down and given, I need a 1/3 there to get rid of that 3, so this becomes 1/6 x squared plus 1 to the third plus c. Safety tips. Incredibly important. The fancy one trick only works for constants. Never for variables. If a variable is missing from the pattern, then you don't have the pattern in the first place. You can't force the pattern by incorporating variables. Important safety tip number 2, and I've said it a couple times already, these are tough problems. They take thought. Slow down and check your answer by taking its derivative. Write it right in there along with your homework. If it takes you a couple extra pieces of paper, then so be it. But you want to be good at doing this. This isn't one of those things that you want to just say, I think I got it, and move on. You want to know for sure that you're strong at doing this type of math. Your grade will thank you. Pattern recognition is like the, I don't know, Excalibur sword. It's pretty good, but it's not as good as the adamantium sword. They're still both pretty powerful, but adamantium is the best in the game.
Adamantium sword took off Wolverine's claws.
That's right. It's the only way to beat them. Okay, change of variables is like the adamantium sword. It's the master sword instead of the wooden sword. Whatever game you want to draw an analogy to is fine with me. Pattern recognition evaluates integrals that are involving the chain rule types of problems. To do that, we look for a pattern. A function composed of a function with the derivative being multiplied on the outside. If you saw that pattern, you could undo the chain rule. We can also solve these types of problems by not looking for a pattern, which is nice. Once you learn how to do that, then you're good. Let u equal that inner function. So off to the side, you'll write let u equal whatever it is. Then take the derivative of it. Du equals your derivative of the inner function dx. Write it as a differential. So if you do that, and you substitute all this stuff in, then f of g of x times g prime of x dx turns into f of u du. Much simpler to work with this than this. And then this is going to be something that you can actually integrate. Integrate it, tack on the plus c, and then back substitute for what you had in the first place. If you define a new variable, u, and use it instead of the original variable, then what you are doing is called a change of variables. And it's very nice. So notice in this problem that we have u equals g of x. Du here means take the derivative with respect to x. But you're going to write it as a differential. You're not going to write it as du over dx or u prime. You're going to write du equals the derivative and then dx. All right, as usual, there's a procedure to follow, lots of rules. Once you get familiar with the rules become kind of a no-brainer. But I'm going to give them to you anyway so that you have them. Method is more powerful than simple pattern recognition because it allows you to calculate integrals more efficiently and more accurately than before, without having to sit there and think, okay, I need this 1/3 because there wasn't a 3 here, and so on. On the left are all the rules, your tips for using a change of variables. Choose a u equals g of x. Make it a good one. A lot of times, it's going to be obvious what that u needs to be. But sometimes you're going to try one and it's not going to work so well. That's fine. Try it again with a different u. Most of the time it's going to be some sort of interior function, or if you have a bunch of terms raised to a power, it'll be all those terms that are being raised to a power. Then find du equals g prime of x dx. Just take the derivative of your u with respect to x. A lot of the times you're going to then solve for dx, but sometimes you might not solve exactly for dx, and we'll see examples that in which you should not solve for dx. Substitute that in for dx in the original equation. If necessary, you might need to solve u equals g of x, the function that you defined as u. You might need to solve that function for x to substitute that in as well. Once you do, all of your x terms and dx term has disappeared. Then you're left with just a function with respect to u and a du. Then you can integrate. Rewrite the answer in terms of x means back substitute. Once you've taken the integral, you can put back in what x was, or what the function was, and then always check your answer. You will want to take the derivative back to make sure that you get exactly what you started with. For example, the integral of the square root of 2x minus 1 dx. Well, obviously I'm going to rewrite that first. Integral of 2x minus 1 to the 1/2 dx. Let u equal 2x minus 1, this interior function, that's right. So off to the side, I'm going to write let u equal 2x minus 1, which means that du equals 2 dx. So before I do that, as of right now, I have u is 2x minus 1. So this whole thing right here turns into u when I substitute that in. I have u to the 1/2 dx. I got to turn that dx into a du. So that's why I'm solving for dx here, because then I'll know what dx is. So I divide both sides by 2, and I get 1/2 du equals dx. So what happens is this right here goes in right there, and this right here goes in right there. I substitute that stuff in. Now I'm going to be changing my variables. So this turns into the integral of 2x minus 1 turns into u to the 1/2. Then dx turns into 1/2 du. And now you can integrate. Much easier than you could here. So, if you notice, this is a constant, the 1/2. I can pull that out and write it out front. 1/2 integral u to the 1/2 du. And that's an integral that you guys have done several times. so now I have the 1/2 still out front. U to the 1/2 turns into what? 2/3 U to the 3/2 plus C. Right? Now if I distribute that 1/2 in, then the 2/3 turns into one-third. U to the 3/2. If I distribute that in though, I get 1/2 C, which is still just C. So I have 1/3 U to the 3/2 plus C. And now we finish off the problem by back substituting. So we say what U was, 1/3 times 2x minus 1 to the 3/2 plus C is the answer. Are we done? Yeah, you need to check. So we want to take the derivative of this. To do the derivative, we need to use the general power rule. So the 1/3 is still there. The 3/2 comes down, times what's inside, which is 2x minus 1. The exponent decreases by 1. The plus C disappears. Simplify. What did I forget? Oh, I forgot the derivative of what's inside, which is 2. Sorry. 1/3 times 3/2 becomes 1/2. The 2 over here becomes just 1. And I'm left with 2x minus 1 to the 1/2, which is the square root of 2x minus 1, which is what I started with. So this is the correct answer.